Good morning, dear students. So welcome to the next lecture of satellite communication, where if you recall in the previous class, we discussed how to find out the range and how to find out the elevation angle and as well as the azimuthal angle. And by taking one example, we have seen that at what different scenarios we can able to find out azimuthal angle. So these are different parameters of the Earth and the satellite as well as sub-satellite point and the Earth station were given. And then we applied the cosine law of the triangle, which we expressed the value of square of any side of the triangle, that is E and ES side. And using this relationship, we could able to write the cos of elevation angle like this. So in this equation, we have taken some uh, values which are constant, like RE stands for the radius of the Earth, RS stands for the orbital height, that is the distance between the center of the Earth to the orbit of the satellite. So we putting those values, we could rewrite the value of cos elevation like this. And then we talk that if we can find out the value of gamma, then hopefully the cos elevation will be known to us. And from that we can find out the distance between the Earth station to the satellite. Okay. And hopefully elevation angle is the main point or main clue in finding the distance or the range of the satellite. So in order to find the cos elevation angle, we have to use the spherical triangle of cosine using this. And these parameters were the latitude and longitude parameter of the sub-satellite point as well as the Earth station. These are the points which these are the coordinates which will be given in the problem or in the example. Using that, you can easily find out the value of cos gamma. And if I take the satellite is a geostationary Earth orbit satellite, so for that the LS value is equal to 0. So LS stands, capital LS stands for the latitude of sub-satellite point or latitude of satellite as well. So in that particular case, we can rewrite the cos of cosine of gamma with this equality. So from this, we can find out gamma as well as the elevation angle. And from the elevation angle, we can find out the distance between the ground station to the satellite. And we also had taken one example. Suppose a satellite is given and a satellite is INSAT satellite, which is located at a coordinate 83 degree east longitude, 0 degree north latitude. And the Earth station is having the coordinate 78 degree east longitude and 22 degree north latitude. The question has been asked to find the Earth station elevation angle to INSAT satellite. Okay, that is the question to find the elevation angle. So we have calculated the value of elevation angle, which is approximately 58.9 degree, that we consider this as very close to 60 degree. And we also had a conclusion that if the satellite is an geostationary Earth orbit satellite or geostationary satellite, you can call. And if any base station want to communicate with the satellite in the geostationary orbit, so the DTH antenna should be elevated at an angle of 60 degree. If we consider the ground surface as a flat, so considering the ground surface as a plane, we have to tilt the DTH antenna at an angle of 30 degree. That means from the ground we have to make it 60°. Okay, if you make it fully 90°, then hopefully it will not happen, but we have to make it 60°. And as you go towards north, that means in Jammu Kashmir, Himachal Pradesh and all, so there you have to tilt it towards little bit down, or 1-2 degree, or up to 5 degree tiltation you have to make towards the ground, because you are moving towards north. And even if you are going to further northern areas like Russia and European countries or North America, and they will have very less elevation angle in order to make a communication from the DTH to geostationary Earth orbit satellite. Okay, so the problem is those locations are the DTH antennas which are present in very northern hemisphere, um, hopefully at an latitude of 70-80 degree north latitude, and similarly 78 degree around south latitude also. So for them the elevation angle will be very less, and if there will be any obstacle, if there are high raised buildings surrounded by any particular antenna, so they will face the signal degradation, or the quality of signal will be very less for those particular areas. So as our country is placed in such a good location, so even if we are surrounded with buildings, and so we are getting good quality. And you know that our country is a very high density of population, and the buildings are very closely packed. So even if in that particular scenario we are getting good uh, quality of signal from the uh, geostationary satellite. Okay. Uh, and in order to check that also, you can change, as I have said, if the base station will be not, if the ground station will be much in the northern hemisphere, that means your latitude will not be 22° north. You can take in place of 22°, you can take 72° or 80° like this north, or 72° south also you can take. So using this value, if you calculate, if you recalculate this for the value of elevation, you will see the elevation angle will be very small here. So that also you can verify uh, here as well, because we are considering this as 72. So in place of 22, this you have to take as 72. And you know that as the angle, at the cosine of the angle, as it increases, means as the angle increases, cosine of that thing, or as theta increases, cos of theta will decrease. Okay, so this result of cos gamma will be less. So once cos gamma is less, means gamma value will be higher. Okay, so you will have a higher value of gamma. So once you put that value, that means here sine gamma, as well as this one, it will be to the power gamma. If you refer the equation, this one, okay, sine gamma divided by this cos of gamma over here to the power 1/2. So you will have a very small elevation angle. Okay, and after that we found what is the azimuthal angle. So azimuthal angle, we know it is the angle which is calculated from the north longitude in a direction towards east. All right. So always you have to calculate in a direction towards east. So that angle is called the azimuthal angle. So in order to find the azimuthal angle, you have to find an intermediate angle. That intermediate angle we consider as tan of alpha. So it is also as a function of the coordinates of your Earth station as well as satellite. So see, the tan of alpha is equal to tan of small le minus small ls divided by sine of capital Le. So as I have said, all three parameters will be known to us. So from that we can find out the tan alpha value, and hence we can find the alpha. So alpha will be tan inverse of this. Now, in order to find the azimuthal angle, we have to follow a given table. So first of all, we have to decide whether the Earth station is in the northern hemisphere or the Earth station is in the southern hemisphere. Okay, so that to find out whether the Earth station is northern hemisphere or the southern hemisphere, this we can find out from the latitude value. If the latitude of the Earth station is given some angle of north, that means it is northern hemisphere, and if the latitude is given some angle in south, that means it is in the southern hemisphere. So for northern hemisphere, that means if your Earth station is in northern hemisphere, okay, so once you verify the first condition, then you have to check for another two conditions. So whether the sub-satellite point is towards the east of Earth station or the sub-satellite point is towards west of Earth station. So if the sub-satellite point is towards east of Earth station, then the azimuthal angle will be 180 degree minus the intermediate angle alpha. But if it is no, that means the sub-satellite point is western of the Earth station, then the azimuthal angle will become 180 degree plus alpha. So alpha is the intermediate angle. The same thing if it is in the southern hemisphere, you have to decide, verify these two conditions from the latitude and longitude of the Earth station and sub-satellite points. So here you have to check, here the values are different, but if you check here, the first, if the sub-satellite point is east of Earth station, then the azimuthal angle will become equal to the intermediate angle alpha, else the azimuthal angle will become 360 degree minus the intermediate angle alpha. So this is how, so whatever angle you are getting, okay, so whether the answer is 180 degree minus alpha or 180 degree plus alpha, or it is alpha or 360 degree minus alpha. So whatever angle you are getting, so that angle should always be calculated from the 0 degree longitude directed from the north towards east. Okay, so consider this is the globe, or this is the earth. So this represents the 0 degree longitude. So this is the north and this is south. This is east and this is west. So from this direction you have to calculate. Okay, so if I take an assumption, suppose I got for a particular example, I got alpha is equal to 50 degrees. So alpha is the intermediate angle. Okay, and when I verified the condition and I found that the Earth station is in the southern hemisphere, suppose Earth station is in the northern hemisphere. Okay, that means suppose my Earth station is here and sub-satellite point is here. So this point is the Earth station. This is sub-satellite point. So sub-satellite point and the satellite both have same coordinates. Okay, so this particular line represents 0 degree latitude. So my Earth station is in the northern hemisphere. And while checking the other two conditions, like whether sub-satellite point is east of Earth station, let us check. This is the sub-satellite point and this one is the Earth station. So sub-satellite point is towards east. So that means this second condition, this one is satisfied. Then your azimuthal angle will be 180 degree minus alpha. So alpha is 50 degree. So 180 degree minus 50 degree. So you will get 130 degree, with that is equal to, this one is the azimuthal angle. So I told that azimuthal angle will be calculated from the north. So if you calculate from the north, so this one will be in 90 degree. So 90 degree plus 40 degree. Okay, so this line, okay, this one is the azimuthal angle. So this angle represents the azimuthal angle. That means in this direction, your satellite is present at an latitude of or at an elevation of angle EL. Okay, so in that means in that angle at an elevation angle, the satellite is located. Correct. So that is what to find out the location of the satellite. So two ways to find the location. One is from the latitude and longitude. Another is from the elevation and azimuthal angle. Now next, we have to find the satellite visibility. So satellite visibility means in two different ways we can think it the visibility of satellite. Suppose any point is on the Earth's surface. Suppose that point is a reference point. Consider the reference point can be the Earth station. The reference point can be a human standing on the Earth's surface, or it can be any point which is a reference point on the surface of the Earth. So satellite visibility indicates for how long duration that particular reference point, whether it is human being or it is any earth station, can able to see the satellite. Okay, so that is called the visibility. So when we talk about visibility in a layman's language, so it is not that we can see the satellite. We cannot see the satellite. Okay, being a human being, some satellites, of course, we can see, but we cannot see most of the satellites. You know that some natural satellites are visible, but artificial satellites, we cannot see them. So when I said visibility, that does not mean that I can see it. No, I refer to visibility means I refer that any base station can be able to make a communication link from the satellite to the base station, to the ground station. So that is what meaning of visibility. Okay, and if the satellite moves to some other location, then uh, we are out of the coverage of the satellite, so we cannot able to communicate with the satellite. So that means we are not within the visible range of the satellites. We are not in the coverage of the satellite. So that is the meaning of visibility. Okay, so it is not that seeing by seeing the satellite or the satellite can see us. It's not like that also. Okay, so when we tell the visibility, particularly if we take the satellites which we are called as geostationary Earth orbit satellite. Okay, so geostationary Earth orbit satellite, they are orbiting on the geostationary Earth orbit or the um, geostationary orbit. Okay, so those satellites, they remain stationary. Okay, or that is called, they are relatively stationary. That means for a particular reference point on the surface of the Earth, the satellite will be visible throughout the year or throughout the duration the satellite is active, or throughout the lifetime of the satellite will remain visible to the reference point on the Earth's surface. Getting the point? So suppose a satellite, this is the reference point. Let us take an example. Okay, so or this is the satellite reference point, or any reference point if you take, whenever there is a satellite and that satellite is a geostationary satellite related to the reference point, this satellite remains stable. So the position of the satellite will not going to change in any instant of time or at any time moment, it is not going to change. Whereas some other satellites, if we talk about like lower Earth orbit satellite or medium Earth orbit satellite, or some other satellites are there also. So their position will change frequently uh, from time to time. So in that particular case, we are launching a series of satellites. Okay, not only one satellite in the orbit, so many satellites will be moving, and all satellites are of same type. So in that case, what happens if any satellite moves moves away from a particular location, then the next satellite will reach at that point, so that a continuous link we can establish. That we have discussed in the very beginning of communication, satellite communication. So those satellites we named as low Earth orbit satellite and medium Earth orbit satellite, and those are launched for the application like remote sensing application, as well as some navigation applications. Okay, but for the communication purpose, whether television communication or any even mobile satellite communication, those satellites are launched in the geostationary orbit satellite, which are relatively stable. Okay, so here we have to calculate the visibility. That means if there is a satellite and that satellite is a geostationary Earth orbit satellite, how much portion on the surface of the Earth will be under the coverage of the satellite? Okay, so to do that, I have considered a point. That point is S. That represents the location at which the satellite is. Getting my point? So at that point, the satellite is present. Now, if you note here, this is the point which represents the yard station, or the point on which the yard station is present, and this one is the point that is called the center of the Earth. Okay, now this is, I can call as the radius of your Earth, and this distance RS, the line joining from the center of the Earth to the satellite, this distance we call it as the orbital height of the satellite. Okay, that means if the orbit is an circular orbit, then the orbital height represents the radius of the circular orbit. And let me take, if I will make a triangle, the line joining between the center of the Earth and the Earth station on the surface of the Earth and the satellite, if you make a line joining between all 3 points, I can make a triangle, and this triangle is an right angle triangle, and the angle I have considered this as a beta. So in this right angle triangle, I can write cos gamma, where this angle is cos gamma. Okay, and assuming this, of course, this one is the right angle triangle. So cos of gamma is what? Cos of gamma is RE divided by the hypotenuse. So hypotenuse is this CS. So RE divided by RS is your cos gamma. Getting the point? Then next thing, for a satellite to be visible, the RS should be greater than RE divided by cos gamma. That means from this equality, I can find the value of RS, that is equal to RE divided by cos gamma. Getting the point? So this is RS. RS means it is the orbital height of the satellite. All right. Now, what is the minimum value of RS such that the satellite can communicate to a point E? So this E point is the Earth station we have considered. This is E point is your Earth station. So what is the minimum value of RS so that the satellite can able to communicate with this? if I will, if I assume the satellite is suppose here, okay, instead of this, I will assume the satellite is here. Okay, then in that case, this satellite will not be able to communicate with this point. Why it cannot be able to communicate? Because the satellite is below the horizon of this earth station. Okay, this particular line represents the horizon of this. So satellite is below the horizon. So the satellite will not be visible to the earth station. The earth station can see up to the horizon. Okay, so below this it cannot see. So even the satellite will be here. So which is the point which is uh, at a higher distance from this, then this point will be under the visibility of the satellite. So satellite can be able to communicate, so, because it is lying above the horizon. Okay, so that is why the value of RS should be greater than or equal to RE divided by cos gamma. So now what is cos gamma? That is nothing but RE divided by RS, and we know RE is equal to 6378. This is in kilometer, that we call as the radius of the earth, and RS is the orbital height of the geostationary satellite, which is around 42,164 kilometer. So this ratio will give us the value of cos gamma. From this, we can calculate gamma as cos inverse of 0.1514, which is around 81.3 degree. So which is this angle, we got 81.3 degree. And if you note here, the triangle we have considered is it is a right angle triangle. So from this we can find out the value of beta. So beta, since it is right angle, so now the gamma plus beta will be 90 degree, and we have obtained the value of gamma, which is 81.3 degree. So beta will be how much? 90 degree minus 81.3 degree, which will be 8.7 degree. So this will be the approximate value of beta. Hope you understood. Now, suppose the satellite is here. So in this direction, it can see, it can cover 8.7 degree. Similarly, in this direction also, it can see 80.7 degree. Okay, getting my point. So suppose a point is there. Okay, don't consider you know suppose assume the mobile tower. Okay, so if mobile tower is located, this is the mobile tower which is located where I will assume it is located somewhere in Rajangunde. Okay, so in this direction it can make a coverage, and in this direction also it can make a coverage. The same way, you can think that if a satellite is here, in this direction it has the visibility, that means it can have coverage, and in this direction also it can have coverage. So if in this direction the angular coverage is beta, similarly in this direction the same angular coverage will be beta. Okay, so in total it will have a total angular coverage of 2 beta. All right, so 2 into beta, if we have obtained 8.7 degree, so 2 into beta will be 17.4 degree. Okay, so if we calculate the total solid angle, it will be like this. Okay, if it is the satellite is there, here beta it will cover, here also another beta it will cover. So if we, this is not the three-dimensional image which you are seeing. This is the triangle. Okay, so like it will make a conical thing on the surface of the earth. Okay, so that we can calculate the solid angle. So these many portions on the surface of the earth will be under the coverage of the satellite. Okay, and where this angle is the total angle will be 2 beta. So any base station which is lying within the solid angle of 2 beta, that will be under the coverage of the satellite. Okay, and we consider this particular satellite as a geostationary satellite. Our discussion or our findings are particularly based on the geostationary satellite. Why? Because if you note here, the RS or the orbital height we have considered 42,000. Okay, so if we subtract 6,378 from the value of 42,000, then you will get something around 35,000 something you will get. And 35,000 or 36,000 approximately kilometer is the altitude at which the geostationary satellites are moving. Okay, it's not the LEO and MEO satellites. LEO satellites is around 1,000 kilometer. MEO satellites are around 20,000 kilometer. So when we took 42,000 as the orbital height, so uh, be sure that we have considered the geostationary satellite as an assumption for this analysis. Okay, so that is what or that is how we calculate the visibility angle. So the Earth station at equator can see a satellite within an arc of 81.3 from its longitude. Getting the point, but what the meaning of where is the pointer? Yeah, what is the meaning of plus or minus 81.3 degree? Earth station at equator can see satellites within an arc of plus or minus 81.3 degree. If I take this is suppose the Earth, and Earth station at equator. So this represents the equatorial line, and this line represents the longitude line, which is the 0-degree longitude. So this is 0-degree longitude, and the equatorial line will be 0-degree latitude. Got? Now, Earth station is at equator. So where will be the Earth station? It will be on the equator. So I can take my Earth station here. Okay, and so if I'm taking, suppose the longitude of the Earth station will be suppose 20-degree what, east or west? Obviously it will be east because I am taking eastward direction. And what will be the latitude? Obviously latitude will be 0 because it is on the equator. Equator means 0-degree latitude, so by default the latitude will be 0. It has only the longitude value, that is 22-degree east. So this is the point where the Earth station is. I will write this is the Earth station. So it is at equator, can see satellite within an arc of plus or minus 81.3 degree from the longitude. Okay, from this is the longitude. As I have said, this longitude is your 20-degree east longitude. So plus or minus 81.3 plus 8. What is plus 81? So 20 plus 81 is how much? 101. So 101.3. So we have to draw 101.3 degree longitude. Okay, so 101 means it will be backside of the Earth. Okay, since I cannot draw that line, but I am assuming, suppose this is the 101.3 degree longitude. So this longitude is what? It is 101.3 degree east longitude. Okay, and what we have done 20 degree plus 81.3 degree. So that is 101.3 degree east. Got it? Because it is in the eastern direction. Now minus also given. So 20 minus 81.3. So what you will get? 20 minus 81.3, what you will get? That means you have to subtract here. Okay, so what you will get? You will get minus 61.3. So there is no longitude which is marked as minus 61.3. So minus 61.3 means in this direction, because you are subtracting this 20, you are subtracting 20, we are subtracting 81.3 from 20. So that means in this direction we are going. So it is at 61. So this line, suppose this line or this longitude is 61.3. So what I shall write? It is west. It is not east because it is westward direction. So the satellite can see how much portion. I'm using a different ink. So this much portion on the surface of the Earth will be under the coverage or under the visibility of the satellite. Where if you note the base station or the Earth station is located here. Okay. This is the location of the Earth station, but the satellite can see this much area on the surface of the Earth. Okay, so got the point. So that is how we calculate the satellite visibility. So I think this one is the last topic. So what is the GSO visibility arc for one Earth station located at 87° east? Okay. One question has been asked based on that. Actually, whatever question it has been asked, we have already done that. But thing is that in that question, it is given the location of the Earth station, that is 87° east. But here we have taken the location of the Earth station as 20° east. Okay, I have taken 20° east as the location. So if you use 87, then one value, one longitude will be 87 plus 81.3. Okay, another value will be 87 minus 81.3. So can you able to answer this now? Whatever which longitude values, that means your satellite can see up to what longitude to what longitude. Can you able to answer this? You see, when you make 87 plus 81, so it will be approximately 168.3. So 168.3. So it is north or sorry, it is east or west, because we are talking about longitude. So it is east or west. So it will be obviously east, no doubt in that, because this is the point. If this is the point or longitude line of the Earth station, which is at 87°. If you add here means you are going in this direction. You are going towards east direction. And if you are subtracting means you are going towards west direction. That is obvious. Now, when you subtract, you are getting 87 minus 81.3. So this result you will get 5.7. So what is the meaning of 5.7? What is the value of 5.7? Whether it is 5.7° east or 5.7° west? What about this longitude? It is 5.7° east or 5.7° west? So try to analyze. The location is where the air station is located at 87. Okay, and you have to move westwise. How much angle? 81.3 degree. Okay, that means from 0 degree longitude, your air station is at 87 degree, and when you are moving back 81.3 degree, you are still in the eastern longitude value. So that means 5.7 degree, it will be east. Okay, but in our previous case, when the air station was in 20 degree longitude, so and you are moving back 81.3. So first you complete 20 and you reach here at 0 degree longitude, then you reach at 61.3. So that means this 20. Okay, let me use a different color. That means this 20 plus this 61.3. This 61.3, this 20. They sum up and it will become 81.3. Okay, so that the new longitude will be 861.3 in the previous case. But in current case, your air station is 87, and when you are moving back 81, still you are not reaching at 0 degree longitude point. You are still lying in the eastern direction. So it will be 5.7 degree east. What is the answer? Yes, the answer is, where is the point? The answer is 5.7 and 168.3. So this is what we also have calculated. So this is the from this longitude to this longitude. That means 5.7 degree east longitude to 168.3 east longitude. The satellite can able to see it. Okay. So I think this is yeah. So with this we have completed some laws of satellite, and we discussed some examples related to find the range of the satellite, find to the latitude, longitude of the satellite, and some terms which are related to satellite communication. Right. So in the next class, when we will meet again, we have to discuss some of the basics of the satellite. That means we shall discuss the evolution of satellite communication as far as Indian space communication is concerned. And we also discuss some of the terms related to satellite communication and some application of satellite communication. Okay. And if you have any question, you can ask me, since I have time. So you can post your question or post your request.